expert has joined the session. Tushar, can you hear me? Dr. Tushar, Dr. Tushar, your mic is mute.
I turned it on.
Yes. Now we can hear you. I welcome you to this second session of the fourth day of 5-day AICT ATAL Faculty Development Program on Finite Element Method for Product Design. It gives me a lot of pleasure to introduce my longtime friend, Dr. Tushar Rajaram Gawawade. Dr. Tushar Gawawade is mechanical engineer by education. He has got his PhD from IIT Delhi in the field of vehicle dynamics and safety. His professional experience is 27 years long. Currently, he is working with TCS since October 2019. Earlier, he has worked with General Motors, Tech Center India, Hindustan Motors, TVS Motors, Post Motors. He has also worked some teaching related assignments at IIT Delhi, SSVPS College of Engineering in Maharashtra, Graphite Company, Gawawade and Kirloskar Brothers in Madhya Pradesh, where we had opportunity to work together for a short while. He has totally 27 years of experience, out of which he worked in production for about 2 years. He was in teaching as well as in research for 5 years each. So about 10 years he has spent in teaching and research, and he has a long remaining experience of about 15 years in automotive industry. He has to his credit, 2 research closures, 8 US patents, and 1 Indian patent, and he has published, more than 10 papers in national and international journals and conferences. He loves to talk and work on innovation, IPR patents, technology development, and testing. With this very interesting introduction, may I request, my longtime friend, Dr. Tushar Gawawade, to, take over the session and begin.
Thank you very much, Dr. Sachin. I thank you for providing this opportunity to interact with the education world once again after a long. I keep getting these opportunities many a times, but somehow with the interest and in the activities in hand, I hesitate to take it up. I could not deny when Sachin asked me. I denied initially, but later on I thought that let me go ahead once again, and then I took this opportunity. And the topic which I'm going to share with you. I'm trying to share my screen. Let me know if you can see my screen.
Yes, you just maximize it. You just maximize it. Yeah, it is visible.
Yeah.
Yes. Nice. Thank you.
Yeah. The topic which I am going to talk with you for maybe 1.5 hours from now. The title is Design, Vehicle Dynamics and Safety, Storytelling. However, all this design, vehicle dynamics and safety is in the automotive context, and even the story is also in the automotive context. That's what I thought that would be the appropriate title, because what I'm going to share with you is a journey which is a glimpse of when the vehicle design starts and finally it lands up in the hands of the customers, and what customers, whether they are they know this field or not, but they are users of it, how is their experience, and that in terms of when they are at the steering or they are not at the steering but sitting on one of the seat in the vehicle. It could be any vehicle, two-wheeler, three-wheeler, four-wheeler. That's the topic which I'm going to talk to you. When I take you through this, I'm not going to get into very details of the things. However, I would like to answer the questions if somebody has the questions. I would like to remain at the surface of it to tell you the story from design till the vehicle safety in the automotive context. The contents of my discussion are, as I talked, design automotive. Uh, I'm going to talk, the next topic is CAD. Then what it includes would be the topology, general arrangement, systems, parts. This is the world which mechanical engineers know it very nicely. Uh, then I take you to the vehicle dynamics, lab testing, field testing, and finally, after the lab and field, which is a practical, we come back to the computers for the simulation, and all this work finally has to have the intention that the testing in the field or in the lab, day by day, it should keep on reducing. So finally, what we intend to do is we take this lab testing and simulation to the level of validation, and thereafter we try to reduce all the resources, maybe it is material, cost, and human effort. Uh, the last topic would be I take this learnings of vehicle dynamics to the world of automotive safety and how the safety engineers would uh, understand it or how they would require it. When I say that design automotive, what uh, this topic is primarily, uh, when I'm going to share this some of the text with you, these are not my definitions or these are not the definitions of the engineers. These are the very general definitions which Google gives you. And I treat Google as guru for most of the knowledge today. It has a huge database, and the uh, information shared is in general accepted, validated by the crowd, and I go by the wisdom of crowd. So the information what you would find in the text would be in terms of the definitions would be the Google information. Uh, what design is? It is primarily concerned with developing and creating the visual appearance or aesthetics of the vehicle. So it's a process of it's not an event. It goes through the iterations of development and creations to give the visual and aesthetics appeal to the vehicle. That's what this design world talks about. This design is not to be confused with what generally mechanical or electronics or any hardcore engineers would be talking as related to the component. It has relation to the visual and aesthetics of the vehicle. This is the field of art. As I said, this is the field of art. Who are these professionals? These are the professionals and designers with the art background, and they deal with this topic, which is design. uh, they translate the requirements or the descriptions of business people or engineers or the customers to a language which is related to the appearance and aesthetics. So these are the designers with the art background. What's their education? They are in general industrial design, but not restricted to. Somebody who does not have a formal education of industrial design, uh, maybe undergraduate, postgraduate, or anything, whatever you say. Uh, the people with the art background and the formal education in India, at least, it is industrial design and Abroad, they call it as transportation design also. So these are the people who work with visuals, aesthetics. They are industrial designers, and they have a background which is arts background. That's a little about what design is. Uh, what I'm showing you is uh, how this design people's area, they call it as many places as design studio, how it looks. On the left hand top corner, it is a car model. People are looking at it. These are the industrial designers. What are they doing? They are sketching, and this sketching medium could be pen, paper, pencils, or it could be modern days softwares like Elias. Before I go to this thing, from the automotive context, how this flow works is that there is a vehicle architecture. The architectures of the vehicles are upfront known, and every manufacturer tries to keep these architectures to minimum. What architecture means is a skeleton of the vehicle. So the investment is minimum, and from one skeleton they develop multiple programs. So in the context of vehicle, it could be hatchback vehicle, it could be notchback vehicle, it could be sports SUV vehicle. Those are the different programs, and these programs could have a different visual appeal. So on the same sedan platform or hatchback platform, they could develop the different vehicle bodies. So different programs originate from one architecture. So companies will have minimum architectures, multiple programs. So every year they keep refreshing that thing. And this is the world themes, which is basically the design, what this designers are working. And what they do when the uh, vehicle architecture gives birth to different programs, these different programs, when they are getting discussed, the industrial designers, they try to capture what is the intent of the management, what is the intent of the company in terms of some keywords. And those keywords could be uh, the company needs aggressive vehicle, it is gentle vehicle, gigantic vehicle. What it could translate is that aggressive means somebody could interpret the aggressiveness of the vehicle as it would have a sharp lines in terms of its outer skeleton. Gentle means somebody could translate this to in terms of how it is operated. The uh, handles, or maybe all the interfaces with the vehicle, they are at appropriate position. And in terms of the forces, if that person wants to translate, it has to be minimum. Now you will say that how the designer would translate it to force. If you say that if something translate, the mechanism remains the same, and then the handle is designed nice in terms of its curves and that thing, it would look gentle. If it is with the corner shapes, the triangular or rectangular geometry, it could look aggressive. So the designers translate the language or the opinions of the people, wishes of the customers, into a language using these keywords. Now, after the world of designers, there comes the engineering, the hardcore engineering, where the vehicle gets translated to various systems and that thing. And finally, it goes to the testing and manufacturing. So, not to get into many details, coming back to the designers world, what do they do? These are some examples. Somebody say that vehicle looks curvy. So this is the some sketch. Initially, they come out with some line diagrams. So this looks curvy to me. Somebody says that it's fluidic. These are some examples of fluidic vehicles. Somebody says that it's gigantic. It looks to me broad. Somebody says that it is stable. Yes, it is broader to me. It looks broader. Somebody says fluidic. These are fluidic. Somebody says that it's sharpy. So I see a notch here. So some these multiple sketches are developed by multiple creative designers, and they translate the language to the sketches, and from sketches it goes to the clay models. These are the clay models they develop. They develop different scale models, from smaller ones to the bigger ones to the full scale ones. So this is a specific clay. With the clay they develop it, and this is done as the physical reality, which is translation of the sketches to some 3D object. Now, coming to from that happens with the exterior. Does the industrial designer's job ends there? No, they get into the interior of the vehicle also. Now, interior of the vehicle, what it means is that the vehicle has so many systems inside it. Now, somebody says it's a stable vehicle. How do I translate that stable? If my vehicle seats look to me or feel to me that little tougher in terms of its stiffness, it is stable to me. Somebody says that I want a comfortable vehicle. Somebody can translate that comfort to the sponginess of the seat. Somebody can translate that gentle in terms of the steering wheel, how it looks in terms of the dashboard. So these are the translation of the company's requirement in terms of various systems, and that's the way it goes from exterior then to interior, from interior to individual subsystems. This is an example of one of the thing which it's a body. So for body, this is some kind of renditions what they prepared. After a brief of design, I get into the world of engineering. What engineering world, they also develop some kind of models, prototypes, and layouts. What are these models, prototypes, and layouts? For the engineers, these are either the prototypes made with the metal, wood, or some material which is a physical world, and they translate that to initially non-moving parts. Then they create the subsystems which has all the mechanisms and that thing. Before going to the details of that, they also use some terminologies. All these engineers who translate, automotive engineers, mechanical engineers, or electronics engineers, or so on, or mechatronics, the topology, the way in which constituent parts are interrelated or arranged, that's the thing. And in general, from vehicle to vehicle, these do not change a lot. However, there would be innovations in terms of these arrangements, and making this arrangement makes the vehicle unique in terms of maybe the engineering aspect or maybe the customer related aspect. The engineers developed the GA drawing, general arrangement drawings. It presents the overall composition, how the different systems are arranged. Now, when I say system, what it is a set of things working together as parts of a mechanism or an interconnecting network. So what I mean systems here is that for the automotive vehicle there are various systems. As you see on the right hand side, the vehicle called a car, it has different systems. Now those systems are front and rear suspension, steering system located here, the powertrain is here, moving from going from engine, gearbox, through the drive units till the wheels and tires. The braking system, you have the ABC pedals here, accelerator, brake, and clutch pedals here. So that's the braking system here. The rigid chassis, it includes the frame, which is the basic on which everything is put on. The seats are included. For the electrical engineer, those are electrical systems. For the safety engineer, those are safety systems. So there are so many systems. It's a complex machine which has approximately 30,000 parts. It's a huge in terms of the parts and systems. I just take one example to show you what it is. Now the steering, the customer looks at the steering as a D-shaped steering, maybe three arms, three spokes to the steering, and on the top of that there could be the interfaces for the customer, which are called as horns. From there, these are the visible things up to the steering column. After the steering column, it goes into the underbody of the vehicle. So it goes to the rack and pinion steering arrangement, and then finally through this tie rods to the steering system. uh, why I am showing these things, because in the next topic we are going to need these systems as connections of the parts in terms of their joints and their points. uh, this is another system which is called as a suspension system. Suppose if you look at this system which is called as a wishbone, double wishbone. This is one wishbone which is called upper, this is a lower, and it is connected with this hub part. There is a heart of this suspension system which is called as spring damper assembly. Now it has one hole here, second hole here, third hole here. All these are the interfaces with the other systems or other parts, and these points are called as the hard points in the simulation world. And this uh, hard points are translated to the markers, so that somebody, if he is interested to know the forces, motions in those respective frames, they are attached at the center point or along the axis of this. So this is another system called as suspension system. This is a bigger picture of suspension system, where you see almost many of the things getting included here. Here the wheel is there. The wishbones, the double wishbone which I talked, this is upper wishbone, this is the lower one, and then connected with a suspension at this point. This is the right hand side, the left hand side. Similarly, you see a steering rack and pinion arrangement here. So the steering column would go from here, and this is a rod which connects left and right side. This is the stabilizing bar, or which takes care of the load distribution transfer from left and right side. Uh, and the wheel is attached here. And these are the points where the frame is getting attached. Now, all these points of attachments are required for it to connect it with the next system. As I talked earlier, the vehicle is a combination of multiple systems. So all these individual systems are modeled by the CAD designer, and initially as the parts, and from parts they are connected appropriately with proper orientation and location. Uh, so once the CAD designer's job is over, what happens is that uh, the vehicle dynamics aspect, if it is to be evaluated, before getting into the subject of vehicle dynamics, let's talk about what vehicle is. It's a thing used for transporting peoples and goods, and especially we know these vehicles as cars, two-wheelers, carts, trucks, or any of those, maybe the land vehicles. When I talk about dynamics, it's a branch of mechanics concerned with motion of bodies under the action of forces. So it has to deal with the forces. The branch which deals with the uh, mathematics and motion and forces, which I talked here, branch of mechanics. So what is mechanics? It's a branch of applied mathematics dealing with motion and forces that finally produces the motion. So here the motions are concerned, here the forces are concerned. There is something called as multi-body systems. When I showed earlier, there are different parts. Those different parts are different bodies. So that's multi-body system, bringing that system from the earlier thing. A study of dynamic behavior of interconnected rigid or flexible bodies. When I say rigid or flexible bodies, it is by a definition, the rigid bodies will not have any deformation under the application of uh, uh, practical known forces, and flexible bodies means that under the circumstances of practical range of forces, they will go under some uh, uh, deformation, which is not permanent. Those are flexible bodies, so they remain within their elastic limit. Each of these may undergo large translation and rotational displacements. So while moving on the ground or on the system, they move a lot, and their rotations are a lot. What does it mean? They move a lot means they move from one place to other place in terms of meters, kilometers. Rotations, they move from smaller degrees to 360 degrees or even take multiple rotations. So multibody dynamics, it's a dynamic behavior related with interconnected rigid or flexible bodies, and it deals with basically the large translation and rotations. As we saw, we have multiple systems interconnecting as vehicle assembly. The parts are connected, we get subsystems. Now the subsystems which we talked earlier are, if you talk about the transmission system, in transmission system you will have engine. Engine itself will have multiple systems. Then another system will be the gearbox, then another will be the drive shaft, then the wheels, tires. So that way multiple systems are there in the brake system, and finally this brake system is a part of vehicle assembly. So this is so many parts, approximately 30,000 parts give rise to so many systems, and finally you have one assembly to deal with, which is vehicle, and this vehicle is used by the customer in terms of its feel. Now that feel could be a comfort or it could be a handling aspect. Now for vehicle dynamics, you really don't need these parts which are having the exact geometry, and the visualization of all those parts has to be the realistic is not necessary. And once when I say this thing, I already introduced you to the concept of the components have the joineries, different joints. So if we know those joints, their locations, orientations, that is good enough for the vehicle dynamics engineers to proceed with. However, when the vehicle dynamics results are getting interpreted, the visualization of all these parts adds to the reality, and somebody who is not from this world uh, can understand, and that somebody who is not from this world is the people who do not deal with vehicle dynamics. However, they understand the subject. They are from the automotive background. Now, why do we study the vehicle dynamics? We study vehicle dynamics to understand the behavior of the vehicle, as I said. Why understand that? Is my vehicle safe? Is it comfortable for occupant? Now the occupant, here the vehicle moves on the road, so it has to take care of the pedestrians, the animals outside the vehicle. So it has to be uh, safe in terms of the occupants, as well as it should not harm the outsiders if at all the situation or circumstances arise. So that requires the understanding of the vehicle dynamics. Now, as we said, vehicle dynamics, it is to deal with the forces which are generated from the vehicle and motions. After understanding what is next, we improve the aspect intended. What are the aspect intended? For the vehicle dynamics engineer, it could be the handling of the vehicle. For the safety engineer or the crash guy, it would be safety of the vehicle. Somebody who is from the uh, vehicle subsystems called seats, they would look at comfort of the vehicle. Somebody who is from noise and vibration background, they look at the noise. So there are so many disciplines and expertise which are required to design this vehicle. Now all these inputs of the vehicle dynamics uh, for respective discipline require different input output. So all those different input output systems are modeled in the vehicle dynamics, and intended output, as I said here, safety, comfort, performance, noise, those are the outputs, and these outputs are post processed by the respective engineers. Now we have started with design. We are now into vehicle dynamics, and later on, as I said, we'll be going into the safety or performance. So we started with why this vehicle dynamics is required, and we on this slide we reach to uh, what it is, or what next for this. Uh, how do we do this journey from vehicle dynamics to the next stage, which is of the safety aspect. Now, for vehicle dynamics, there are two aspects. One is the vehicle simulation, which happens inside the computer labs, and it includes the systems and full assemblies. So those are simulations carried out with the vehicle assemblies. For the testing people, it starts in the lab, it happens in the field. Those are called as proving grounds or test grounds. And finally, all this work which happens inside the lab, in the field, they need to be correlated. So finally, we end up having only the simulation world, or maybe the uh, CAD models, mathematical models of the vehicle systems, and we remove or eliminate or reduce the world. Why do we need to reduce this? Because the cost involved in this is too high. Effort involved in this is too high. People involved in this is too high. And uncertainties are also very high. When I talk about uncertainties of this world, that is the place where this world dominates in terms of the engineering discipline. When we get to the slide of the validation, I'll come back again to my statement of this world of testing dominates, and that is called as the expert riders, and they have a very high importance in terms of what they say, and what they say has some understanding of their experience, which they do it in terms of thousands of hours with the vehicle. This output of simulation, output of test world, they are brought to the single platform during post processing, and we call that as comparing with each other. That's a correlation. Now when we correlate the simulation model initially with the test model, there is some deviation. If that deviation is uh, too large, we call it as a bad correlation. If that is within acceptable limit, we call it as good correlation. Now, what is this good and bad? I see this as a descriptive terms. So, initially, the correlations in terms of the outputs are uh, compared subjectively. Once the subjective nature of that outputs are matching, then we go to the objective nature of it. What it means is that we go to the magnitudes of those plots. What I'm talking is that when we have this testing and simulation, all these things finally we plot it in terms of simple graphs. Those could be a 2D graph where x-axis and y-axis will be there. Suppose it's a spring. For spring we plot it as force and displacement. So force and displacement of the spring in the simulation world, force and displacement from the lab world, brought to the same graph where x-axis is displacement, y-axis is force, and we see that how is the subjective nature of it, and then go to the objective nature, that is the specific magnitude of that force with respect to different displacements. So then we call it as good or bad correlation. uh, the action of checking or proving the validity or accuracy of something is called validation. That's what I described here as good correlation and bad correlation. And the things which are correlating good, the models are updated so that the correlation is taken to the maximum limit or acceptable limit. The world of maximum limit has gone today. People call it as acceptable limit, and within the acceptable limit, if it is there, then it is good to take the decisions and move ahead. We don't look for increasing the correlation from 90% to 92%, 92 to 93, and 94, and so on. If 90% is there, in many of the situations, the things are good to go ahead to take the decision. And that's the importance of doing the simulations. You get the quick results and quick directions to move ahead. coming to the next aspect of it, which is a testing lab. Now, in the testing lab related to the vehicle, what do we do? For testing of the vehicle, we look at various parameters. I have listed few here. The mass of vehicle or mass of parts, mass of subsystems, center of gravity of all those things which I talked about, parts, subsystems, and then the vehicle. The inertia related aspect, that moment of inertia. Then for suspensions, we call it as K and C. K stands for stiffness, C stands for damping. The tire characteristics. This is a very complex world, and even the people who are experts who wrote the book on tires, they also do not claim that they understand this component 100%. They still say that they are learning. Uh, Transmission characteristics and steering gear ratio. So these are different terminologies, different characteristics which are required for the uh, vehicle dynamics to be understood, and these are measured in the test lab. I am just showing one example of suppose I have a vehicle assembly. Now with this vehicle assembly, I need to know at the vehicle level where is the center of gravity of this vehicle. This is the extract from the IS standard 13849. This is a four-wheeler. The front axle is here, the rear axle is here. The distance between the two along the length is called as wheelbase. The left hand side and right hand side of the wheel, distance between them, it's called the track. And there is a center of gravity which is here. Now the distance between the front axle to the CG is termed here as X. Distance between the CG and then the rear axle is termed as Y. The CG height from the ground is called Z. Now, if I want to find out the distance of this CG with respect to the vehicle in its coordinate system, wherever it is located, I'm interested to know its location along the wheelbase and its location along the height. Now, from the simple practical world, we know that if I have some object which looks like this, I want to know its center of gravity. How do I find out? Experimentally, what do? I will take a flexible string, tie it around that object, and when it is stable, the string, if I extend that string from vertically, on this line, the CG would lie. I rotate this, or I go from the, I mark a line on this object then. Suppose this is some stone. So I mark this line extended and then mark this line. I go to the other side of it, maybe right hand side or left hand side, and then I mark a similar line on that. So all this three planes, when I club it, I would get an intersection along this vertical line. Now, if I am interested to know this CG height from this point to this point, what do? I'll untie this object, tie it at some other location, maybe along this, and do the same thing. When I do the same thing, again the object would suspend like this, and the CG would lie on the string. Using the same technique, the center of gravity for this vehicle will be evaluated. Now, I'm just showing one tractor which has this as the front wheels, these are the rear wheels, and you don't have to get into so many variables here. What you have to look at is this capital W is the total weight of the vehicle, RF, which stands for the reaction from the front wheel, and this X1 is the wheelbase here, and X2 is the distance from the rear axle to the CG. Now we know that from the, if we write moment about, suppose this point, this uh, capital W into X2 will be equal to this X1 into RF. So finally, X2 will get this equation. Now X2 would lie on this line, which is vertical line, and the total weight of vehicle would stand to pass through this. So I got W this x2. Now I'm interested. I found out its length along the horizontal axis. I am interested to know its height. So what do? I lift the front wheel. After lifting the front wheel, what I said here, or what I said in terms of the this object, which is called a stone, stands true here also. So instead of suspending, what I did here, I have lifted it. You can suspend also. Uh, uh, it is easy for me to lift. So after lifting this thing, again my weight would pass through the CG. Now this x2 which was here is modified to x2 dash. The wheelbase which was here has modified to x1 here because of this tilt. Now the same equation appears to me as x2 dash is equal to rf dash x1 dash by w. So my x2 dash would lie through this. Now I mark a line, vertical line through this x2, and wherever my earlier line was here, this is my earlier line and this is new line, that is the point of cross section, that is my G, which is center of gravity. Now same thing, if you do it across the uh, left and right tires, you would get its location along the lateral direction. But in most of the cases, this center of gravity for the vehicles is at the central median plane. So it doesn't differ because the systems are symmetrically placed. It is quite in close proximity to the central median plane. Now, next parameter which we talked about was the inertia. Now for inertia, we learn in our theories that a simple uh, concentrated mass attached with inextensible string with length L, and if we give it a small oscillation, what it means is that we remain in the bounds of this sine of theta equal to uh, uh, approximately equal to theta in terms of radians. So if we remain that maybe in 3-4 degrees as the oscillation, so if we plot all those, if we do this experiment, this is the theory which tells us that the torque equal to I into alpha. I is moment of inertia, angular acceleration. Finally, what we get is we get the time period for this simple concentrated mass. This time period, through all these equations, it is related to the inertia. In the practical world, we don't come across this kind of objects. We extract the theory of this to the real world. Now this is a real world. This is one of the test labs from IIT Roorkee, and this is a two-wheeler. What they have done, they have one string attached on this side, other string attached on this side, and this is another way of measuring the moment of inertia. Now, how to measure the moment of inertia? We talked about simple pendulum. There is compound pendulum, which is distributed mass, not like this as a concentrated mass. And in our coursework, uh, if you are from mechanical engineering background, in theory of machines and mechanisms, we talk about compound pendulum, and then we generally take the connecting rod, which has two eyes, big eye and small eye, and do this experiment. Then there is something called as bifilar suspension. Bi stands for two. So one string here, another string here, and it is given the oscillation in the horizontal plane. So it oscillates about somewhere this axis, imaginary axis is here. There is something called as trifilar suspension. When we say that this is bifilar, there are three strings put to it, and then the platform rotates about its vertical axis. That's a trifilar suspension. For vehicles like car, which are huge in terms of area and mass, they either they are put on this kind of platform, and then they are given the oscillation in this direction. So this point A is the point of axle, which is frictionless axle, and it is connected with the strings here, which are again inextensible strings. The purpose, when I say inextensible string, the purpose of inextensible is that this L, which we are saying, remains constant. That's the meaning of inextensible string. We don't will land up in a complex world when this L keeps on changing. When we have a freedom to keep it simple, keep it constant, we do that. That's why this is inextensible string. And for a platform which is empty, the inertia is obtained by this equation. It goes through the derivations of all those things, and finally this is the thing. When you have a car put onto it, the car mass goes into this equation, which is m car here, and you get the inertia about axis passing through CG. So similarly, for getting, the car will have three inertias: uh, roll inertia, pitch inertia, and yaw inertia. As you say, when the car moves left and right, up and down, that's the roll. Car keeps moving up and down with respect to its front end and rear end, that's a pitching. The car keeps turning, that's a yaw inertia, and then the products of inertia also would be there. So this is about the one method. The other method is that a tri-pillar suspension. The CG of the platform is here. We measure the car CG and we coincide that with this. And once we do that, we put the car onto it and we give the rotation, which is again into a smaller oscillation. And with this thing, we measure the time period. So this is T is a time period without car on the platform. Ti is the measure the time period with Ti is without the car, and T is with the car. And finally, you have all those parameters. M car comes from the mass of car, Mi comes from the platform of the car, L comes from the length of the strings, and others are, the things, gravitational constant and pi, these are the constants. So this is another way of measuring the moment of inertia. The other systems in the car are called suspension system. Now in the suspension system, you have springs. As I talked earlier, you get the force and displacement. Now in a simple method, what do I do? For the spring, if I have this spring initial, I put a weight onto this, it gets compressed. Now I have the weight, I know the displacement of it. Finally, the spring stiffness is nothing but force upon displacement. So I plot that thing, and this graph is showing as one slope, another slope. This is a stiffer, initially softer. So the car springs or bike springs, they are in general the dual rated. Bike springs are dual rated, and in some of the vehicles they put spring into spring. Actually there is no need, but however what they are trying to achieve is that you get a softer spring and stiffer spring combination, and there is something called as progressive rates. So the stiffness, instead of looking at a linear line, it looks as a multiple lines connected together. This progressive term is common in terms of the spectacles also. There is a progressive lens. What they do, they vary your number in terms of the vision which you move. So it's quite synonymous to that. Coming to the next, which is the damper. Now, the spring which I showed in earlier thing, the spring is, this is coaxial thing. The damper and spring, they are coaxial. For measuring the spring stiffness, the damper is made absent. How to make the damper absent is that you take out the damping fluid from the damper out, drill it, take it out. So it helps you in guiding the spring, and you measure the spring displacement, and the force transducer will be there. So you get spring stiffness. For damper to measure, you take out the spring from the damper and then put it here. At the bottom of this, what is there? There is a motor, and the motor connecting rod is attached to this, and this damper keeps moving up and down. Now we know that something is rotating with a radius r and angular velocity omega, it would reach to a velocity as v. So v equal to r omega, that's basically the velocity. And the dampers characteristic is force on the y-axis, and on x-axis there is a velocity. So The velocity comes from this equation, whatever is the rotation speed of that motor and radius at which it is attached. So it is half of the stroke. So particular to that velocity, what is the damping force? That damping force is plotted here. One is in the tension and other is in the compression. So from this suspension measuring machine, you get the curves like this. This green curve is for one velocity, red one is for higher velocity, next higher blue, then magenta color. So all these things you plot it as the force displacement for the force velocity curve for the damper. On the top side, it shows the uh, tension, and then maybe the compression on the other side. Next is in terms of the tires, which I talked about as a complex thing. Why it is complex? Because the complexity comes from its construction. See the complexity. There is a tire bead which actually is moved onto the wheel rim while mounting. There is an inner liner, then the first ply, second ply. There are so many belts here. First belt, second belt, the side wall is here, and tread is here. What we see as a nice design pattern is a tread which actually is in interface with the ground, and then the side walls are not touching, they flex, and with the side walls it is connected with the wheel rim. So it's a hollow construction with air filled into, and that air should not leak out, so you have a bead here. So for tire testing, which is a complex of, and these are metal belts in some of the cases. So it's rubber, it's a cotton plies, it's nylon plies, it's a metal plies, and finally again rubber, which is a which has the silica compound also into. So the tire is represented as a disc here, and for tire, this is the lateral axis for tire. The normal force represents the vertical axis. It is rotating about this axis, which is showing the angular velocity, which is spinning, and tire is supposed to go in this direction, which is perpendicular to this lateral and normal force, but it doesn't go into this direction. It goes into a slightly different direction when you apply the steering. So the wheel travels in this direction. And why it happens? It is as a geometry heading towards this direction, but going in this direction. However, this angle shown is very amplified. It is small angle. This happens because of all this construction. There are other parameters listed here for the tire. Now, this tire testing, this is a tire stiffness testing machine. What it does is that you have a tire filled with some pressure. Now the stiffness varies along the tire pressure. When you feel more air pressure, you feel it more stiffer. If you have less air, you feel it softer. So based on what tire stiffness is required, for that tire stiffness, the different air pressures are related. Now for those stiffnesses and that thing, for the vehicle dynamics engineer, you need the tire stiffness. Tire stiffness is, again, stiffness is force upon force by displacement. So how much force you apply to the tire and how much it deflects, that is measured on this test rig. Now there is something called as resistance. Now this resistance is sliding and rolling. In terms of this tire which is rolling onto the road, we are interested in terms of the rolling resistance. For this rolling resistance of the tires to be measured, comparatively a bigger drum is taken, and on that drum this tire is rotated. Theoretically, if somebody can make this drum as flat as road, that would be the reality. So the tire is tested on this comparatively flatter platform, which is a drum, and you get the rolling resistance here. This is again one of the test rigs from IIT Roorkee. For the educational institutes, they develop this kind of test rigs in-house, and for the industries, they could develop or they could purchase also. This These things are developed as a part of research initially when the labs are developed, and those become the projects for engineers as well as the faculties working on there, and the learnings of that thing go into the research. So from this tire, you get various properties. Now, what are those tire properties? You have various properties called as longitudinal force, lateral force. So the tire, when it is moving straight, you experience the lateral traction at the tire. When you are taking a turn, that time the lateral forces come into picture, and vertical force is basically from the load which is getting applied and which is changing with respect to the tire rotation, vehicle rotations, transferring from one wheel to other wheel, that is fore aft or on the side directions. So all those forces, they are measured with respect to the different variable which is on the x-axis. There is something which is very well known in the world of tires, is called as magic formula, and this magic formula was designed by Dr. Pajeka. And this formula, when you do not have most of the data related to the testing, it goes by some research which they have filled into, and this kind of tire models are available in the simulation models. So it has these different constants, D, C, B, E, all those constants, where these constants are derived based on the research, and this research is for specific tires of different sizes, so smaller and bigger tires, and for that you get this Y property. Now, what is this Y property? Y property is the property on the Y axis. It could be longitudinal force, normal force, or lateral force, and X is what? It could be the slip. What is slip? I earlier talked to you that tire is supposed to go in this direction, but it travels in this direction. That is called as a slip. So all those things are put into, and you get the different tire properties. What are these different tire properties? As I said, it looks like as a lateral force here. This is a aligning torque, and the longitudinal force. If you see, the nature of these two curves are similar. Why it is similar? Because it is those are lateral and longitudinal forces. As the nature of this two curve is similar, it is possible to capture that by a single formula which could have different constants, and that's the work which is involved in this magic formula. Now, when all these things happen in the test, who does this testing? This testing is done by the expert riders in the field. I'm talking about the vehicle level testing. And this evaluation by expert rider, it goes majorly by their feel and experience of their input. Now, what inputs these people give to the vehicle? When they are on the vehicle steering, they give the steering maneuvers. They have other controls in their hand as ABC pedals, accelerator, brake, clutch, and different gears. So with respect to all these inputs, which are the driver given input, they give it to the vehicle, and to that input, how the vehicle reacts is their feel. Now, why their feel is important? Because their feel is not related to one vehicle. It cuts across all the vehicles produced by that company. And not only that, every company purchases the vehicles of their competitors or from the different world of vehicles, and they drive that and interpret the behavior of the vehicle. And this behavior of the vehicle, apart from the experts, the general customer also drives, and general customers' expectations, feelings are captured, and their feelings are translated into the understanding of expert rider. Uh, what are these different testing? This different testing involves, these are the standard testings. This is a skid pass. On the skid pad, what happens is that the vehicle is driven into a circle. When the vehicle is driven into a circle, this circle radius, they keep it constant, keep reducing, keep increasing. So that's the skid pad. The name comes from skid pad is that if you keep the speed constant and keep reducing the radius of this circle while driving, at one point of time, the centrifugal forces make the vehicle skid. That's the skid pad. The figure 8 turn, as you see, the shape of this test track is like number 8. And when you see this as 8, it looks as two circles, but when you drive it as a vehicle, you are moving from here. When you go here, you take a right turn. When you move here, you take a right turn. Come back again to the center. Now, when you go into this circle, you are taking the left turn. So it's a combination of left and right turns. Here, it's only one kind of turn. The person, if he takes goes into the opposite direction, he will have left turn converted to the right turn. So both the left and right turns are combined here. Now they are into the constant radius circles. This is constant radius circle. This is again constant radius. One may be bigger, other may be smaller. For the slalom test, this is a proving ground or the test tracks. On the test track, these are different roads which has different road curvatures as well as different road width also. And through this, the vehicle is passed. The person who is testing, he takes the vehicle through this slalom test. The world of vibration engineers, they look at, or durability engineers, they look at what how the vehicle reacts to the disturbances of the road. So this is something called as Belgium pave. So these are the Belgium blocks, and these Belgium blocks are giving the input to the tires, and through tires it goes to the vehicle and even to the occupant sitting through the steering and seat and all other interfaces. This is another big system which is a proving ground which I talked. All these white lines which you are seeing, these are different tracks, and on these different tracks the vehicle different properties or response to different inputs, steering input is tested. You see on this left hand side there is a straight run. So on the straight run, what you can do, you can test how fast the vehicle goes, how it reacts to the braking, acceleration, the aerodynamic properties, and that thing that you test here. This is a constant circle radius. There are so many other things here inside as small paths. So all the input combinations are checked here, and these proving grounds are very big. And in terms of the facility, bigger companies own this, or the proving ground itself is a bigger testing agency which does only the job of providing this track to the manufacturing world, car manufacturing world, and they maintain this thing. Now, in terms of the geometries of the road, these are different geometries. In terms of the surface texture of the road also, they have different textures of the road. There is something called as split mu. Split mu stands for two coefficient of friction. So one of the car wheel will face a higher coefficient of friction, other would face low coefficient of friction. Now, practical world, how it matters, when you are moving on the road, one of the wheel is on the road and other goes on the soil. So that's a different coefficient of friction. So those kind of realities are mimicked here. This is another test track where the car is moving on the slope, and you see this in the movies many a times. Coming to the other bigger topic of research in terms of the maneuvers and handling, this work was started sometimes in the 1999 or 2000 time frame. NHTSA, National Highway Traffic Safety Administration, which is the US agency which has developed this standard maneuvers for vehicle handling, What are the standard maneuvers? This is a single lane change. When the vehicle is moving on the straight road, if it wants to overtake, it takes a lane change and it goes here. This is a one lane change, so it goes here. Uh, this is a double lane change. After overtaking, if the vehicle wants to come back to its original track, it goes from here, overtakes, and then comes to the original track. There is something called as J maneuver. This looks like a letter J. Vehicle goes straight, takes a right turn, and it goes through this J turn. This is a fish hook turn. Uh, if this J turn is little deviated from this, so when the vehicle is moving here, first the left turn is taken, then the right turn is taken, and then vehicle goes into the curvature. So here only the right turn is there. Here it goes through the combination of left and right. So all these different combinations of steering turns vehicle will experience because of its inertia different throw for vehicle as well as the occupants within. And uh, for this, the output parameter what is monitored in most of the studies is that whether the vehicle goes into rollover. What rollover is? Vehicle goes one of the set of wheels, which is the inner wheels, gets lifted because of centrifugal force, and the reaction on the inner forces goes to zero, and the vehicle goes into the turn. Vehicle rolls over. So the intention of this most of the maneuvers is to study the rollover behavior of the vehicle for the vehicle dynamics engineers. Now coming to the other part of it, testing, field testing with the dummies. What we talked here is earlier that all this turns, the somebody who is an expert rider sits into this. Now, as we said earlier, the intention is to uh, get rid of most of the cost related to various aspects. Now, one of the aspect is that test riders and testing people. So can we eliminate them? We cannot, but we can standardize their understanding in terms of the engineering parameters. So for that, we have the dummies which behave all the time same, because the dummy remains the same, and these dummies are for different testing, they are validated. For testing, SAJ 211 is the standard, and part 1 is used for electronic instrumentation, part 2 is used for photographic instrumentation. The electronic instrumentation is something which is required to capture all the parameters which we talked earlier, the force, displacement, maybe the velocities or the angles. All those things are uh, measured with the electronic instruments, and for that what uh, instruments you need the force transducers, you need the torque transmitters, you need the LVDTs, and so on. For photographic instrumentation, you need something called as camera. This camera, how to use and what speed, frames per second it has to have, what orientation it has to have, what all angles it has to capture, all those things are decided, and then it is standardized. So there is a standard part 1 and part 2. Part 1 is for the electronic instrumentation, other part is for the photographic instrumentation. Some of you might be knowing all these things. I'm showing this just for reference that these dummies, it's a family of dummies, because the car occupants, vehicle occupants, they range in terms of their size and age. So if you want to capture the behavior of those things, or capture some signals from them or their experience, you need individual dummies of those sizes. So this is complete dummy family. Uh, and for the study is 95th percentile male hybrid 3 dummy, which has 6.2 6 feet 2 inches tall and 100 kgs. is the weight. And for fifth percentile female dummy, which is basically a fifth percentile male dummy, which is height 5 feet and 50 kg. Here, 95th percentile, the 95 represents that 95% of the population is smaller than this. 95% of the population is smaller than this. When you say 5 percentile, 5% population is smaller than this. For the human body, if you look at human body as a mechanical system of different parts attached together, you see the human as head, the human has shoulder, it has the chest, it has lower arms, and other parts. Like all these parts, something called as uh, biomechanics, the world of this mechanical engineering, for the biomedical engineering, all the components uh, of the mechanical system, they are tested in the simple terms as spring dampers. So for human body, the spring dampers system is model, and these dampers and springs, they are not linear, they are highly non-linear things. So for all those components, different frequencies which are mentioned here, 20 to 30 hertz, based on what mass it has, what spring stiffness it has, those are the frequencies, and these frequencies are known from a well-established study over the years. And these frequencies has a relation to the frequencies which come from the vehicle. Now, if I have something coming from the vehicle in terms of 20 to 30 hertz, it would be very sensitive to my head. So I need to treat that frequency at least for my head. I need to shift that band, or from the vehicle side, or from the other path of the load. What is the other path? From the vehicle, it comes through seat to me. So on the seat, I do some treatment in terms of changing these frequencies and move away from those frequencies, so that I do not excite these natural frequencies of the different parts. These are the different natural frequencies for different parts. And sometimes people feel that, hey, in this car, I feel uncomfortable, I feel like vomiting and those kind of things. So it has something related to the system called as human system, and for that human system, those different frequencies, if they get excited, it causes a trouble there. That trouble is unwanted. So the vehicle designers, coming from either the system complete vehicle level or system level, they handle these things, and at the design stage itself, they are well taken care of. These are different frequencies. uh, in general, when we get all this data, we get the data in which has a lot of noise, and for that lot of noise, the signals, as we saw earlier, lot of graphs, they are smooth graphs, but when you get the data from the experiment, they are not so smooth, it has lot of noise. So all those noise needs to be taken out. The frequencies which are of interest, they are to be only considered. So the signal processing is other world, which after the data is captured with all the data acquisition systems, the data needs to be post-processed. For post-processing, there are various filters, and these filters has different theories in terms of the frequency class response and that thing. So for which component of the head, if we are interested, we take the signal from that component, and that component, I'm saying that if it is head, there is a sensor into the head. If it is a component from the chest, the sensor from the chest, that signal is taken. And you can see that it is, these are modeled as different components. The lower leg, then there is a knee, there is a joint here, similarly the ankle joint here. So all those components, they are fitted with the sensors. So the signal from those components are post-processed, and for post-processing also there is a nicely developed theory, and those input is available in SE J211. This is from electronics parts thing. While post-processing those signals, you need to take care of the units, because for validation you need to be in the same unit. The simulation signal, experiment signal has to have the same units. Output location, in terms of experiment, when you do the experiment, you have limitation in terms of locating the sensors, because the sensors are physical sensor. They have some size, shape, and finally it needs to take the data acquisition card out of that. So there are some limitations. So those output locations has to be matched in the simulation. In simulation you can put the sensor anywhere and then define its mathematical formulas or whatever is the input output by locating it at a point. That limitation is not in the simulation, but for practical world you have the limitation. So practical world where the sensors are there, that you need to match here. In terms of the coordinate system, the coordinate system for vehicle, uh, they follow the SAE coordinate system, and for that SAE coordinate system you need to match the coordinate system into the simulation also. If they do not match, in the post processing you need to match, you need to flip those axes to match. And finally the data filtering, all those frequency class and all the data need to be post processed so that you come on the same platform. Coming to the simulation part of it, vehicle dynamic simulation, this I'm showing. These are from the Adams software. This is showing as a full vehicle assembly. And in this, you can see the system here as steering system. There is a suspension, tires on this side, and on the rear side, you have the rear tires. And this is a complete vehicle body. It will have a frame here. This is another picture of the simulation. Now in the simulation, initially we talked about the suspension system, and I showed you some points which are the joints, axis. So those points are of importance. So this is one of the hole in that lower arm. This is another hole into the lower arm. This is third hole into the lower arm. And this 3 points, if we have these 3 points, we just connect them as 3 lines and call that as a link. In simulation is okay. You don't have to have the physically looking very similar part into the simulation, but in terms of its coordinates you need to have that correct geometry. In terms of only the hard points, they call it as hard points. And markers, markers are nothing but something like this triad XYZ. What this XYZ are, these are the axis. So this axis needs to be oriented here, because for this axis, if we are interested to know the rotation of this lower arm, so rotation in what, about what axis and what frame, so you need to locate that thing, and that rotation from the test has to match with this. So you need to locate that looking at what the experimental sensor location is. So this is the spring damper which is modeled here, and a 3D model looks like this. You have a spring damper with this bottom joint here, and these joints are of different types. These joints could be maybe the revolute joint, maybe the translation joints, universal joints, spherical joints, and so on. In case of the steering wheel is rotating here, so you will have one turning pair here, you will have one universal joint here, because the two axes having included angle, and you have to translate the rotary motion. So you need a universal joint here, one, another one here. At the bottom, whatever is your steering, you apply the steering as full one rotation, but finally the wheel rotate by only small degree, so that steering gear ratio is involved here. So it is reduced here, the steering gear ratio is here. It has for the simulation, it has hard points. Hard points are nothing but, as I already talked, as different joint points, or the points which are for uh, different uh, interfaces. Those are the hard points. uh, there are different parts and different joineries. So this is about the steering joint. Now, all these subsystems, you test it initially as subsystems and then as a vehicle system. All these subsystems are tested individually, validated with the test results, and validated subsystems go into the vehicle. The test rigs available uh, in the simulation are slowly increasing steer, J-turn, road edge recovery, single lane, double lane, whatever we talked earlier, including that steering pad test, number 8, all those things are available in the simulation also. So you don't have to model that test rig here, and those are called in the simulation language as test rig. Those are standard tools available, and you get into. This is one of the output of one simulation which goes into the J-turn. Vehicle goes into the J-turn, uh, follows this path on the road. What it means is that vehicle, this is the steering input on the y-axis. So the steering is increasing. It keeps constant for some time and then reduces. In terms of the path, steering is constant here. Then you apply that steering. Keep the steering constant means this steering constant means radius of circle is constant, radius of curvature is constant, and then you reduce means the vehicle will come out of the curvature path and will head to the straight. So this is the curvature reducing, similar to this, and this path which is straight, that comes here. For all these things, the different uh, outputs are taken from the uh, vehicle sensors in the simulation. So these are some outputs. Generally, you will see this kind of curves which are symmetrical about the horizontal axis, and they generally represent left and right combinations. Here, the normal force, which is for one of the left wheel, is on the top, right wheel on the bottom. I don't want to get into the details of this analysis. Coming back to the when you have uh, the simulation and test results, the correlation what I talked earlier, uh, output of testing and simulation are correlated here. For correlation of this, when the outputs are having some deviation, we as a vehicle engineers, vehicle dynamics engineers know that which parameters contribute to what behavior. So they keep updating those parameters. And what are those parameters? As we talked earlier, the CG locations, the mass, suspension, tire, all those properties, those are updated and they are taken close to the practical values as and when we test. But initially we don't have all the test values, so initially we start with guess values which are available from the earlier vehicle or from some research, and as and when we get the data from the testing, we keep adding that and then remove the deviation between the actual numbers in the simulation with the practical numbers, so we improve the correlation. Once the correlation is acceptable within acceptable limits, the model becomes validated model. Now this vehicle dynamics and testing experts opinion matters. As I said earlier that the expert rider opinion matters. Why? Because it's a clear cut difference from the uh, reality versus simulation. The reality, when we are doing simulation, we go by standard steering angle, what steer rate, uh, and in terms of the time domain, it is fixed. But in terms of the practical world, there are n number of combinations of all those parameters. So for every parameter, you can't test the vehicle as a test engineer on the proving ground. For all parameters, simulations can be run, but simulations, as these are very heavy models, it takes time. So in this kind of situations, how do we do? Instead of doing thousands of experiments, we take the outcome, and based on some representative outcomes, we categorize them and go by the limited number of experiments. So this limited number of experiments, we do it in the simulation. However, these experts, they have run this vehicle or similar vehicles or other vehicles from the competitor from for so many years. So there they have all those number of experiments as their database into their mind, and that's why it matters. So finally, the opinion of this expert riders has the importance, uh, and it is a kind of give and take for the simulation and in the testing world. But finally, when it comes to the feel effect is majorly goes by the expert riders. Coming back to coming to the next topic, which is the safety of the automotive. Now, this vehicle dynamics inputs are taken to the next level. Automotive safety, it's a study and practice of design and construction of equipments and regulation to minimize the occurrence and consequences of traffic collision involving motor vehicles. So it basically safety, we are talking about if at all the accident happens, or if the accident should not happen, what kind of safety for the person inside or outside the car, living being, can be minimized, the damage to be minimized. So there are two terms which come as active safety and passive safety. Active safety means actively we do something so that the accident will not happen, the skidding will not happen, rollover will not happen, the crash will not happen. So the technologies which help in assisting preventing this crash, those are active, that's the active safety domain. Passive safety, if at all vehicle does not have the safety active safety features and vehicle meets the crash or vehicle rolls over, or having all these things also, the input from the occupant or input from the environment, because the environment input in terms of the road ditch, road holes, road protrusions, the road surface, those are not in control of the occupant. So if at all something goes beyond occupant's control and it goes into the crash or rollover, the damage to the human as a property, human life has to be minimized. So the features which are designed to minimize that thing is called as a passive safety. And for that active safety, you have so many systems which are from the active world. I don't want to, my intention is to just show this thing, not to get into all these technologies, but namely few. If your car has heads up display, so you uh, don't end up looking into multiple directions to know that how the road is. So on heads up display, it gives you the complete picture of it. uh, the other systems, those for your interest, I'm listing here. Getting into the passive safety, on the passive safety system side, the vehicle structure, the seat belts, airbags, and all other components which could reduce the damage to the occupant, they are listed here. So the passenger safety cell, crumple zone, seat bags, airbags, and that kind of thing. Now, output of vehicle dynamics goes to the safety study, as I said. What it means is that we have that validated model from the simulation. That validated model from the simulation has state variables. Now, what are the state variables? As we said, the coordinate system as X, Y, Z. Along this X, Y, Z, displacement, velocity, acceleration, or anything like that, those are, or rotations, those may be translation or rotation, those are captured from the vehicle dynamics model. Because vehicle dynamics model, they take into account large rotations and displacement. When it comes to the safety model of the vehicle, it includes FEMESH, and this finite element models, they are much slower in terms of running on any big machine, and it takes huge time. and they do not handle the large displacements. So how that gap is breached? You take the vehicle dynamics simulations output, and that output you give it to the CAE model, and that CAE model you make it roll over or crash with uh, the object, and finally check out what are the injury parameters to the occupant. And all these inputs which are from the vehicle dynamics state variables are used to design this passive safety features as well as active safety features. Now uh, for active safety feature, if I want to take the example, there is a vehicle moving, and if the vehicle is going to roll over, what it means that you assume that car as a flat plate moving around along horizontal, and if it tilts more and the rate of tilt is more, you guess that it is going to roll over. Now for that rollover, you need to save the occupant. How to save the occupant? Retract the seat belt so that occupant does not move away from the seat. Deploy the airbags so that if the occupant comes and hits with the hard objects of the car, occupant is saved. So that roll and roll rate, all those inputs are available in the vehicle dynamics model. And this vehicle dynamics model inputs are fed into something called as black box of the car, and they are called as sensing diagnostic modules. So that black box gets all these inputs from the uh, simulation, and based on that, at what outputs, maybe the uh, rate of the output, means roll angle or roll rate, or yaw angle and yaw rate, all those rate dependent output, those are calibrated, and based on that the safety systems come to the rescue of the occupant, they deploy. That's what I wanted to take you from the design through vehicle dynamics and finally to the safety aspect of it. If you have some questions, I'm open for it as the time permits. I'm open for your questions and comments.
Okay. Thank you, Tushar, uh, for your nice and informative lecture. Now, dear participants, if you have any questions related to the discussion that is presented by Dr. Tushar Gawawade, you can ask him quickly, because we are running slightly late in the earlier as well as this session. So maybe we can take one or two quick questions. One question has come, Tushar. I'll read it for you, sir. The tire stiffness testing is done when the tire is stationary or in motion, and whether the road conditions are analyzed on tire at the stiffness testing machine.
Yeah, your question is basically tire stiffness at stationary tire or rotating tire is one, and road conditions. For stiffness, the road conditions doesn't matter, but for rolling resistance it matters. And for a sample of rolling resistance coefficient between the drum and tire, it is tested. There are some labs which model that different coefficient of friction based on attaching some linings to the drum, so that the stiffness coefficient of friction is varied. That way, the rolling resistance would mimic the the road properties. The other question was about tire stiffness, static or dynamic. Uh, as you said that when it is stationary or when it is moving, I would say that whether it is static or dynamic. When it is static, it is measured statically. There are ways to measure dynamic also, so it can be measured static and dynamic. Okay, but for most of the experiments, it is static, and this static and dynamic coefficients, they are in close agreement. However, based on the requirement of correlation, it can be taken to the higher and higher accuracies. So to answer your question, yes, it could be done static. Mostly it is static. For road conditions, you can change the road conditions by a road which is your drum, which I showed it in earlier uh, test rigs.
Okay, there is one few more questions. You are requested to name few FEA softwares used in vehicle design and analysis and simulation work.
Uh, for vehicle dynamics, there are many, but I have used Motion View, which comes from Altair, the Adams, which comes from MSC, Medamo, which comes from TN Netherlands, and there are multiple others also. For CAE, what I have used is PAMCrash. I have used, and LS Dyna is also there. If you do a Google search, you will find many, but the choice of which software to use is not yours. It is driven what is given to you. These softwares are expensive, and uh, companies use one software and their models are tuned to that software. The compatibility from one software to the other software is there. However, the people who are in the company, they start using one and they start loving that and start using it more and more. Their interpretations, their comfort level is more with one software. However, if other software gives you better feature, they go to that. So the choice of software is not with you, it is given. So what is available, you have to go by that. And couple of softwares, if you want to know more, you can do Google search. I named a few.
Okay. Tushar, one more question. In similar context, is there any software that you want to, you are using for crash worthiness of vehicles?
Mhm.
You said that, I think, PAM crash and yeah, maybe you can
LS
repeat.
Dyna.
Yeah, LS Dyna
Yeah,
and PAM.
LS Dyna.
Okay, okay. One more, there are many questions. Does the active and passive safety have separate software?
Uh, see, finally, the software is not separate. What you process is separate. In terms of active safety, if you are talking about all those electronic signals and that thing which are received from vehicle dynamics and has to be given to the vehicle, so that if it is related to the braking, the vehicle has to brake. So most of the active thing goes to the electronics world, so that they control all those things before the accident happens, or the accident should not happen. So it goes with the signal. And for the passive safety, the things come mostly to the mechanical world, where if there is, the vehicle goes with some velocity acceleration and it experiences some force, so finally the vehicle structure goes into some deformation. Once those deformations or forces happen, that has to be taken up by the occupant, and a barrier comes in between them called as airbag or maybe the seat belt, which helps them. So these modules are modeled into the vehicles, and based on that, there are different softwares for electronics aspect. Uh, However, all these things, uh, as the things are going more and more towards electronics side, the softwares are tuned to handle these electronic signals also.
Okay. One more question. Is NX software suitable for doing these analysis and simulation?
Uh, if you name particular which NX, I can handle that question offline. But to be very specific, I don't want to say yes or no. It could handle.
Okay. Tushar, one more small question that I have. When you showed
Mhm,
those dummies thing,
mhm.
related to male, you said some 95 as the figure. related to
Mm-hmm.
female dummies, you showed a figure as 5. Why
Mm-hmm.
these figures are drastically different when it comes to male or female uh,
In 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 general,
dummies?
the male is bigger in size than
Okay.
the female, and these things are derived from the male dummy only. So that this fifth percentile, which relates to 5 feet and 50 kg, so 5 percentile of the population will be below 5 feet and 50 kg, and uh, 95th percentile 6 feet 2 inches and 100 kg. So 95 percentile population will be below this. That's the significance of this.
And
However,
those
this
are
female,
the,
yeah, please go ahead.
please. So, and those are the values of the corresponding values which are taken for the dummies.
The dummies are developed. This physical dummies for testing are available with this, and this population 95th percentile and that thing. The survey is carried out, and for based on the survey of uh, huge population, these numbers of height and weight are available. Now, if the question goes like that, the US population is in terms of height, they are taller and weight is more. What about Indian population? Yes, the Indian population, there are some standards which were developed, and I came across in 2000 in ARAI. They have published that the similar numbers for Indian population also. But however, for most of the simulations, they go by this, because this world of dummies that is more progressing and more matured there compared with any country's things. So these things have the research from uh, all the research agencies from the world. And if we think that 95 percentile dummy is taller for Indian condition, you go to the 50th percentile male dummy, which could be 5 feet 8 inches. So in place of 95th
Okay.
percentile, 50th percentile would be used for Indian context.
Okay. Okay. Thank you, Dr. Tushar. There are no more questions. It has interested many participants, as can be seen from the questions. And I saw that you touched upon aspects of industrial design, and began with the basics of that, and then you touched upon points related to vehicle dynamics. You explained us what are the industrial practical testing, uh, and how they are carried out, also what are the various measurements that are taken. And you have also uh, told us that once the testings are finished, there are simulations which are taken, and how simulations and testings are going to complement each other in deciding finally how the vehicle is going to perform. So you know uh, for this informative lecture, which is very difficult to listen for people from academics, because there is not a very good bridge between industry and academics in our country, and the interactions are fewer for, I don't know, for some unknown reasons. Therefore, from that point of view, I feel that it was a very interesting lecture and very informative lecture, and it took us quite away from whatever we tell our students from our books. And an addition of this information, like what you have given, in addition to the knowledge that we have from books, would make our classes more interesting. Many participants have started commenting that it was very nice and interesting session. I, on my own behalf and my on behalf of my institute, thank you for giving us such a wonderful lecture and taking into a different world, giving us aspects of product design and safety in overall sense. I know that it was very difficult for you to find out time, sparing time, and get formalities and permissions from your industry. But in spite of all odds, you could actually help us, and come and join us and could share your long experience with us. Is in fact an invaluable input to this faculty development program. So with these few closing words, I thank you for your help, and wish you a great day ahead. Thank you.
Thank you very much. If at all somebody has questions and would like to interact, they can come through Dr. Sachin. I would be happy to continue this thing and share the knowledge as well as learn from the academics. Thank you very much for your kind attention and good questions. Thank you very much. Have a good day too.
Thank you, Tushar. Bye.
Thank you. Bye.